when we talk about asymptotic unbiasedness, what do we mean by asymptotic unbiasedness, given my preparatory remarks?
The sample is very large, and the estimation of the mean of the sample approach the population mean.
Period. Right. So what we can expect is that, remember in the first semester or second semester of calculus, you talked about the convergence of a sequence. So when we're talking about asymptotic properties, we're talking about what happens to those sequences. So we have a whole sequence of sample means. So the sequence converges on the population mean. Tells us that the sample mean is asymptotically unbiased. Is the least squares sample variance asymptotically unbiased? Wrong. Wrong. Is the least squares sample variance asymptotically unbiased? Oh, maybe I'm asking another question first. Is S squared, or least squared S squared, unbiased? Is that an unbiased estimator of sigma squared? Yes. So in small samples, the sample variance is unbiased. So now we've got a sequence of S squareds. We start over there in that corner. This S squared is based on a sample of size 2. And it goes all the way around the room a few times and out the door and then down there by the dean's office somewhere. There's an S squared that was based on a sample size of 1,000. So what's happening to that sequence of S squares as the sample gets larger? Are they converging on sigma squared? Okay. So the least squared sample variance is asymptotically unbiased. Is the maximum likelihood sample variance unbiased in small samples? No. Good yes. Because the first one we already agreed was unbiased, and the second one is different in the denominator, so it couldn't possibly be. Okay. So good reason. Is the maximum likelihood sample variance asymptotically unbiased? Yeah. Because the denominator is so big, that's subtracting off the one that we have. Did you do that right? Did you do that? The notion of asymptotic variance is the same. We could look at the sequence of our estimator and ask what's happening to the variance of that estimator as the sample size gets large. But Gladys, tell me about the notion of consistency. Consistency, I'm a very consistent guy. I have the same thing for breakfast every day, at least for large parts of the year. Someday you're going to be teaching undergraduates, right? Or you're going to have a career in financial engineering. It's easier to do that than teach undergraduates, probably. So what you say is correct, but it doesn't have much intuitive sense to it. So give us a more intuitive explanation of consistency. As a little bit of help, let's put something on the board. So theta hat behaves that way. It's a little hard to see the hat. So theta hat behaves that way. Is theta hat a consistent estimator? Yeah. Because it means, in your parlance, the explanation you were just giving me, theta hat converges in probability to theta. Right? That's what you told me. So how do we understand what that means? One way to understand what that means is to do the following little experiment. I let you pick epsilon as small as you want. It's your choice. Consistency means that I can find an n big enough so that the probability that theta hat differs from theta by more than epsilon, that epsilon that you chose, is the probability of 0. Or, turn it around. If you tell me the n, then that tells me what epsilon I have to pick. That's the notion of consistency. And conversion to probability. Are all consistent estimators unbiased? Class. No, we got you. You did good. Let's move on. John. Are all consistent estimators unbiased? Yes. We had an example on the board that I erased just before I wrote that. No. Right? We had two versions of the sample variance, right? We said that the least square sample variance was unbiased, but the maximum likelihood sample variance was not. But they are both consistent. So what color is your shirt? You know, in fact, there was somebody, there was an alcohol there. Is that you? Yeah. It seems like what's the same? Oh, no, there's a big difference. This is the definition of consistency. And the definition of unbiasedness, we could, for example, we could ask, what's the expected value of x bar? The expected value of x bar is the integral over the support of x, f of x, dx. And the estimator x bar is said to be unbiased if it's equal to the population parameter of choice. There's no probability there at all. And there's no question about how big a sample size I have to be. The sample mean is unbiased, whether I have a sample of size 2 or a sample of size 100. So unbiasedness means that regardless of the sample size, on average, our estimator is correct. Consistency means that as small as you pick epsilon, I can pick the sample size big enough to make the probability of missing the truth vanishingly small. Does that work? Unbiased doesn't change on the sample size.